Our beautiful HX50 makes you want to fly, and by manufacturing everything in-house, we make it affordable so you're able to fly. Together, we're creating a general aviation renaissance. We call it GA 2.0. For you, it means a breathtakingly beautiful new aircraft, ready for sustainable aviation fuels and connected for the modern world. Our all-new ownership operating system supports every aspect of HX50 ownership, from in-house insurance to comprehensive warranties and power-by-the-hour maintenance to pilot training and active safety management, keeping you and your family safe. Together, we've built the Hill Global Community, a place that provides easy access to the very best that the helicopter lifestyle can offer, globally and amongst new friends. Clearly, the scale of this task is vast. Create an all-new class-leading helicopter. Create a pioneering, affordable turbine engine. Create an all-new digital cockpit. And then create all of the processes and all of the infrastructure needed to manufacture every single part. Then build it, test it, and approve it. Tonight, we'll showcase all of the progress from across the program on how we're delivering on each of those objectives. Producing a next generation turbine engine is a very big deal, but not because it's difficult. It's because it's absolutely crucial to being able to deliver next generation light aircraft at commercially viable prices. Consider this. There's less than £10,000 of expensive raw materials in an engine of this size and type. And the equipment to make these components has never been more readily accessible. And we have it all right here at PC1. Sure, these machines are complex and extremely highly strung, but the design, analysis and testing equipment and the knowledge that we have available today right here at PC1 far exceeds what the guys that did this originally back in the 60s, 70s and 80s had available to them. That's not to downplay the difficulty of the task. This is difficult, this is complex, this will take time. But before we even start, we know that this has been done before. We know how to make this work. Let me take you now through each of the parts of GT50 piece by piece, and I'll show you exactly how we're doing just that. Unlike traditional engines, the GT50 uses a high-speed, high-frequency, high-voltage direct drive starter generator unit. This unit consists of two groups of components: the mechanical assembly, which includes the rotor, the stator and the casing, and then the power management unit, which is all the electronics, hardware and software that control and operate the device. We've now completed the prototyping of the drive shaft. This is the stub shaft that sits on the end of the gas generator and drives the rotor of the starter generator. And then also the stator and windings, so the laminations, the windings, and the wire terminations that come out of the back of it. And with those in hand and the final casing currently on the 5-axis machine, it's time to assemble it and test it. Given that the starter generator runs at 50,000 RPM, it's important that the system is both statically and dynamically balanced to ensure smooth running and avoid harmful vibration. In order to do this, when we designed the rotor, we built additional areas of land on all of the rotating parts that can be subsequently machined away as the system is both statically and dynamically balanced prior to assembly and use on the test rig. With the rotor balanced and the stator electrically tested, the system can be assembled with its casing and connected to its brain, the PMU. In parallel with the development of the flight hardware, we've also been designing and commissioning the specialist test equipment necessary to test and qualify the system, and then building a lab around it. And here it is. This is our fully commissioned high-speed test rig, which is about to start testing the motor and generator functions of both the mechanical and electronic hardware of the starter generator. This system allows us to prove every element of the performance and reliability of the starter gen across a wide range of operating conditions. Over the course of the next 2 weeks, we'll be mounting the first prototype starter gen system on the test rig and running the system throughout its entire performance envelope. And this major milestone marks the first module of the GT50 engine on the test bench and working. Necessarily, much of the time to date on the GT50 program has been spent developing the core elements of turbomachinery. The reason for this is that these are the elements that consume the most technical resources and take the most effort in manufacturing, process development, and infrastructure development. With these elements of the engine now maturing nicely, we've turned our attention to developing some of the ancillary systems that are also required to make the engine function properly. If you now look at the front of the engine and the general state of dressing of the engine, you'll see that there's much more equipment mounted to the front of the engine and around the engine to serve the various systems on board. Let's start by having a look at the lubrication system. Looking at the front of the engine, you can now see that we've added the lubrication system hardware to the accessories module. At the front of the engine, you can see the yellow filter body, the oil pump tucked in behind it, the oil distribution and scavenge lines, and then the oil tank at the bottom of the engine. The filter body at the top contains multiple functions. It acts as the oil filter itself. It has the oil filter impending blockage warning flag, the pressure relief valve, and then also the oil fuel heat exchanger, which cools the returning oil and heats the fuel prior to injection into the engine. When you look across at the oil pump just below the filter body, you can see that we have a 4-chamber gear pump, which provides one pressurized line of oil to distribute the oil to all of the injector nozzles and jets around the engine, and then 3 separate scavenge lines that pulls the returning oil and the returning air oil mist back from various locations within the engine and into the filter body. The oil tank itself is then conveniently located at the front lower side of the engine and contains around 5 litres of oil, which is enough for all reasonable operations. In addition to the lubrication system hardware, we've also now integrated the key sensor elements for the control and instrumentation system. On this image here, you can see the oil pressure sensor, the oil pressure switch, oil temperature gauge, the speed reduction gearbox chip indicator, the auxiliary gearbox chip indicator, and then the rear bearing chip indicator as well, all conveniently located around the engine. In addition to this, we've also got the Hall effect sensors for N2 that are used to pick up the N2 speed, as well as the Hall effect sensors that pick up torque by looking at the distortion of the drivetrain throughout the engine. In addition to this, we've also integrated the engine mounts both at the rear and the front end of the engine to secure GT50 to HX50. GT50 uses a modern annular combustor comprising of roll-formed, superalloy, laser-welded, interlaced rings. We featured the production of these rings and the development of those processes extensively in previous updates. Now, it's time to bring all of that together. Welcome to our precision laser welding facility here at PC1. Over the course of the last few weeks, the guys have been focused primarily on the processes necessary to be able to take the individual rolled rings, assemble them in a welding fixture, and then to create perfect, repeatable, gas-tight welds between each of the layers of the rings that make up the film-cooled combustion sheeting every time. These processes are traditionally extremely labour intensive, so we've been focusing very much on how to jig and fixture these components so that we can subsequently automate them and eliminate the labour content, making the GT50 combustion system as cost effectively as possible. One seemingly innocuous part of the GT50 engine that's crucial to the performance, efficiency, emissions and reliability of the engine is the fuel injection nozzles. Although these components are very small, their internal geometry is extremely intricate, and the conical shape inside that nozzle that's not dissimilar from the internal passages of a funnel are absolutely crucial to delivering the cone angle of spray that we require, the mean and distribution of particle sizes as it atomizes, and the flow rates that we need to guarantee both the minimum and maximum flow through the engine. In order to develop these to the point where we can freeze it for production, we've been doing a series of tests on our laser visualization rig to measure the cone angle from the nozzles, measure the flow rate, and to study the atomization properties of a variety of geometries very close to the target geometry for the GT50 nozzle. Today marks another important milestone in the development of HX50. We've now frozen the primary flight display design for the digital cockpit, meaning that Eric and his team can now get on with the important business of implementing this software on the target hardware, ready for testing before year end. The design itself has gone through numerous iterations over the course of the last 2.5 years, gradually evolving from piloted flight tests, customer feedback, and a consistent pursuit of perfection in terms of combining the best elements of traditional analog gauges with all of the benefits of modern digital displays. The production version of the PFD is crisper, cleaner, and more refined than ever before. Airspeed is now conveniently positioned at the top of the display with a simple curved arc giving a needle as well as a digital display. Our new and novel altitude indicator brings the best of analog gauges and digital readouts while only using one needle to present your altitude, irrespective of how high you are above sea level. This is combined with a large, easy to read vertical speed indicator and the large power indicator that's always been a primary feature of the Hill digital cockpit. The rotor and engine tachometer are now crisper, clearer, and more easy to read than ever before, with the engine temperature and electrical gauges provided at the bottom of the screen and a homogenized communication and transponder bar. As in previous designs, we've also got the pass-through layer that provides video footage as a background from the camera installed in the nose light in the front of the aircraft. And the colour schemes have all been adjusted to work perfectly with this. We've also provided the toned down night theme that makes the contrast more appropriate for night flying so as not to glare in the low light environments. And then finally, we've also integrated with that the infrared pass-through layer to make flying at night safer than ever before. Tonight, we've shown you that the starter generator is being built right now, the test rig's ready to go, and the starter generator testing will commence before the end of the year as planned. Similarly, the avionics PFD user interface has been frozen, the system is being built in the avionics test lab upstairs, and again, testing will start before the end of the year as planned. Early next year, the electrical system, the crashworthy seat, and also the drivetrain will start testing as planned. All 4 deadlines on schedule, on time. We set ourselves an epic challenge: build the finest 5-seat helicopter ever, which in turn needed the most cost-effective light turbine engine ever. To do this, we've had to vertically integrate an entire aerospace supply chain. Sounds like a tall order, and it is. But our factory will be home in time for Christmas. GT50 will run for the first time by the 28th of June 2025, and HX50 will take to the air for the very first time by the 20th of December 2025. GA 2.0 is coming. 2025 is our year.